This story is about a place in the universe where the familiar unit, 1 hour, loses its singular meaning. Not in metaphor, not in beautiful phrasing, but literally. Near a certain object, time for two observers ceases to coincide to such a degree that the very word now becomes dependent on who speaks it. I will speak of a boundary you cannot touch, yet cannot cross back. Of a geometry in which the future turns out to be a direction, not a free choice. Listen to what lies behind this calm description. Near a very compact and very massive region of space, gravity ceases to be simply a force. It becomes the shape of the very fabric of the world. Light traveling outward loses energy. Signals arrive ever more infrequently and ever more faintly. Clocks near the surface tick more slowly than clocks far away. And this is no longer a philosophical question, but a measured effect, confirmed even in the weak fields of our planet. If you mentally bring an observer closer to the boundary, the difference begins to grow. His own processes, the beating of his heart, the ticking of atomic clocks, the motion of molecules, continue exactly as they do for us. But to the outside world, his hour stretches, dims, reddens, and in the limit turns into an almost motionless image. No catastrophe, no flash, no blow. A quiet disappearance of information about a person who continues to exist just as much as we do. And the question here is not only about the hour. The question is what simultaneously means for 2 points separated by curved space. What if the word now has no singular meaning at all for two people standing at different distances from such a region? Not because they failed to communicate clearly, but because the very light by which they exchange signals travels through space where time flows at different rates. What matters more, a second measured near the boundary or a second measured far from it? Listen, this story is about exactly that. There are objects in the universe near which the familiar notion of 1 hour simply ceases to have a singular meaning, not in a figurative sense, but in a literal, measurable one. We will work through this calmly, step by step, because this subject matters not as a tale about black holes as such, but as a precise and calm demonstration of exactly where familiar human notions of reality reach their end. The discussion concerns one of the most robust and at the same time most unusual consequences of modern physics: how time and space behave near objects of colossal mass and extraordinary compactness, which in the scientific literature are called black holes. Before we approach the subject of 1 hour next to such an object, it is important to calmly establish what science means by a black hole. It is not an object in the usual sense of the word, and not a body with clear physical boundaries accessible to the touch. It is a region of space in which the gravitational field is so large that not even light is capable of leaving its bounds. The boundary of this region bears the name event horizon, and beyond it the familiar notions of motion, observation, and the transmission of any signal cease to function as they function under ordinary conditions. Modern physics describes such objects within the framework of general relativity, and in that description, gravity is no longer an ordinary force, as it often appears in everyday experience. Here, gravity is understood as the curvature of the very fabric of space and time. Mass and energy alter the geometry of spacetime, and the motion of bodies and light proceeds through this altered geometry. Near objects of very great mass, such curvature becomes especially apparent, whereas far from a black hole, space and time behave almost as they do under familiar conditions. But the closer one draws to the event horizon, the deeper the changes become, changes that can only be described with the aid of precise mathematical models. One such change is the difference in how time passes for different observers. This is not a matter of subjective sensation or psychological perception, but of a measurable physical effect. Clocks situated closer to a massive object run more slowly compared with clocks situated farther from it. This effect is called gravitational time dilation. It was predicted theoretically and subsequently confirmed by experiments. Under Earth's conditions, its magnitude is negligibly small, but near a black hole, it becomes incomparably more pronounced. Clocks situated a little lower run a little more slowly than clocks a little higher. This is not philosophy, but a measured fact. Now imagine that a little becomes incomparably greater. That is precisely what happens near the event horizon. If we examine the situation of 1 hour next to a black hole, one essential circumstance must be clarified at once. That hour depends on exactly where the observer is located. For a person remaining far from the black hole, and for a person situated near the event horizon, that interval will not coincide. The distant observer may count a very long time while only 1 hour passes at the event horizon. Conversely, for the one who is near the horizon, his own hour feels entirely ordinary, with no internal disruption. All processes appear normal in the local sense, but comparison with the outside world will reveal a significant divergence. There is no violation of logic here and no contradiction. The difference arises from the very structure of spacetime, in different points of which the timescale turns out to be different when observers compare measurements. Near a black hole, space does not simply compress in the ordinary sense. It changes its geometry so that directions and distances begin to behave differently than in an ordinary Euclidean model. If one imagines a ray of light passing near a black hole, it will not travel in a straight line. Its trajectory will curve, not because of any resistance from a medium, for this is vacuum, but solely because of the geometry of spacetime. As one approaches the event horizon, these effects intensify. It becomes ever harder for light to maintain the direction we would perceive as outward. In the region immediately adjacent to the event horizon, all possible future directions of travel turn out to be directed inward. This statement requires careful understanding. It does not say that some external force appears pulling inward. It says that the very structure of possible trajectories in spacetime changes in such a way that traveling outward simply ceases to be an available direction. Near a black hole, time for the local observer continues in its ordinary way. Biological processes, chemical reactions, the motion of particles, all this unfolds in its familiar sequence. But comparison with the outside world shows that 1 hour here is not a universal unit. Among the scientific models, several types of black holes are distinguished. The simplest describes a non-rotating, uncharged object, whereas in the real universe, many black holes appear to rotate. Rotation adds additional effects. Space-time not only curves, but also appears to swirl around the object, a phenomenon called frame dragging. In this discussion, however, it is important not to delve into the details of rotation, but to keep attention on the basic effect of the difference in the passage of time. Black holes, contrary to popular notions in popular culture, do not suck in everything around them at great distances. At a significant remove, their gravitational influence may be exactly the same as that of any other object with the same mass. If the Sun were replaced by a black hole of the same mass, the orbits of the planets would not change instantly. What is key is precisely the proximity to the event horizon. Only there do the described effects of strong curvature of space and time manifest. 1 hour next to a black hole is not a universal unit, but a local interval whose meaning is revealed only in comparison with a distant region where the gravitational field is considerably weaker. As one approaches the horizon, signals from any source become ever less frequent and weaker, and in the theoretical limit, they cease to arrive altogether. To understand why this happens, one must examine how science describes the difference in time for observers located at different points within a gravitational field. In general relativity, time is not a universal quantity identical throughout the universe. It is connected to position in space and to the intensity of the gravitational field. This statement is not philosophical. It follows from the mathematical structure of the theory and is confirmed by experiments in weak gravitational conditions. On Earth, this effect is very small, but it has been recorded. Atomic clocks situated at different altitudes run at different rates. Clocks closer to Earth's surface, where the gravitational field is slightly stronger, run slightly more slowly than those positioned higher. The difference is negligible, but instruments of high precision detect it. Now let us mentally amplify this situation and draw near to an object of extreme mass, such as a black hole. The effect begins to grow, and near the event horizon, the difference in the passage of time becomes not merely measurable, but fundamentally significant. From the perspective of a distant observer, a process occurring near a black hole appears slowed. Light emanating from that region loses energy. Its frequency decreases, and it gradually shifts toward the long wavelength end of the spectrum. This phenomenon is called gravitational redshift, and it is important to understand it correctly. Light does not lose energy in a local sense. In every local region, its properties remain ordinary. The change arises only when one compares different regions of spacetime that have different structures. As one approaches the event horizon, each successive signal from a source arrives later and later and weaker and weaker. For the outside observer, this creates the impression that time near the surface of the black hole is slowing down and gradually freezing. Yet this impression arises from the mode of receiving information, not from any subjective slowing of processes. For the observer situated near the black hole, the situation is entirely different. His local time flows normally. His clocks, biological processes, the motion of atoms and molecules, everything continues in its familiar sequence. He experiences no slowing of his own time. This is an important clarification that frequently gives rise to confusion in popular descriptions. The difference manifests only in comparing two regions of space, when one observer compares his measurements with another's who is far away. In the mathematical description of spacetime near a massive object, a so-called metric is used, which defines distances and time intervals. Near a black hole, this metric changes in such a way that the temporal component begins to behave differently than it does far away. One in the same interval, 1 hour, at different points in spacetime corresponds to different amounts of external time. The closer to the event horizon, the stronger this divergence. Let us mentally picture two observers. One is at some distance from the black hole. The other is gradually approaching the event horizon. Signals from the approaching observer will arrive ever more infrequently, with a growing interval between them, measured by the clocks of the distant observer. For the approaching observer himself, however, his own intervals remain even. He is able to count 1 hour on his clocks and will detect no internal anomaly. If he were to send signals outward and they were to arrive without loss, the outside observer would see that hour stretched. As the horizon draws near, the signals become ever fainter and ever more stretched in time and frequency. In the end, within the framework of an idealized model, they cease to reach the outside observer. And this means not the disappearance of the object in the ordinary sense, but the loss of accessibility of information about the processes occurring near the horizon. Light leaving the region near the horizon loses ever more energy. Its frequency decreases to very small values, and in the limit, the signal becomes indistinguishable from the background. This is the result of a theoretical limit in the equations. No one literally observes a freezing. This is a boundary that arises as one approaches the horizon in the mathematical description. For the outside observer, the object falling toward the horizon never reaches it. It dims and slows, as if forever. From within, nothing special happens. Both observers are correct, and both describe the same event. 1 hour next to a black hole is an ordinary physical interval for the local observer. He can measure it using any local processes. But in comparison with distant time, that same hour may correspond to a significantly larger interval of external time near the event horizon. In theoretical models, this difference can become extraordinarily large, approaching very great values as one draws ever nearer to the horizon itself. The local description always remains continuous and normal for the one near the black hole, whereas the external description becomes asymptotic, approaching a limit without reaching a final value. This divergence is rooted in precisely how light loses energy as it leaves a strong gravitational field. And that same effect does something entirely unexpected to the concept of at the same moment. Atomic clocks at different altitudes run at different rates, and this is no instrument error but a strictly measured effect. Near a black hole, this gap becomes not merely significant but defining. In everyday life, it seems possible to speak of what is happening right now in different places. We intuitively suppose that there exists a single, common moment of time, the same for the entire observational system. Under ordinary conditions, this approximation works well enough not to produce contradictions. In general relativity, however, this conception turns out to be non-universal. The simultaneity of events depends on which frame of reference the observer occupies and on how the gravitational field is distributed. Near massive objects such as black holes, this becomes especially apparent. Different observers located at different distances from the black hole may fundamentally fail to agree with one another on which events precisely occurred simultaneously. And this same effect produces what turns the concept of at the same moment into something meaningful only in a local, strictly bounded context, and not across the entire region near the black hole. What if the word now simply has no singular meaning for two observers standing at different distances from a black hole? Not because they communicate poorly, but because the very light by which they exchange signals passes through space where time flows at different rates. If two observers are at different distances from a black hole and attempt to synchronize their clocks, they encounter the fact that synchronization procedures begin to yield different results. Even if light signals are used for synchronization, the exchange of information already carries within it the influence of curved spacetime. The light carrying information itself travels through a region where time flows unevenly, and so the interpretation of the moment of transmission and reception of a signal becomes dependent on the path that signal traverses. The result is a situation in which it is impossible to define a single, universal present moment for the entire region of space near a black hole. This does not mean that time disappears or becomes chaotically indeterminate. In every local region, it remains strictly defined. The clocks near the observer continue to function sequentially and predictably. But the connection between different local times requires that the geometry of spacetime be taken into account. If one examines 1 hour near a black hole, one must specify, this is 1 hour by the local clocks of the observer, measurable by internal processes that are independent of the outside world. If one then attempts to compare that hour with the clocks of a distant observer, one must account for how light and information travel through curved space. Here, an important effect comes into play. Events that appear simultaneous to one observer may be distributed differently in time for another. In weak gravitational fields, this effect is small and often imperceptible. But near a black hole, it becomes fundamental. The very structure of the concept of now becomes inhomogeneous. Causality, meanwhile, is fully preserved. If one event influences another, that influence remains consistent across all frames of reference. But the precise way in which the timestamps of those events are distributed depends on position within the gravitational field. At the level of the mathematical description, this is connected to the fact that in spacetime, there is no single way to slice it into layers of simultaneous events. Different observers use different partitions, and these partitions may not coincide. Near a black hole, such ambiguity is amplified. The gravitational field strongly influences the geometry of time. The lines describing the motion of observers and the lines describing the propagation of light begin to behave in complex ways relative to one another. If one mentally pictures two signals sent from different points near a black hole, their path to a distant observer may take different amounts of external time, even if locally both signals were sent at the same moment. Upon receiving these signals, the distant observer will register their arrival at different times, and the reconstruction of the true sequence of events will turn out to depend on the model used to interpret the data. In scientific practice, this is not considered a paradox. It is a property of the geometry of spacetime itself. Local processes, meanwhile, remain strictly ordered. Atomic transitions, the motion of particles, biological reactions, all continue in sequential form. What changes is only the connection between different regions of space. 1 hour is always locally defined, but its position in the overall structure of time depends on how observers synchronize their frames of reference. And it is precisely here that one of the most subtle consequences of general relativity reveals itself. The absence of a single universal line of the present running through the entire region of spacetime. Near a black hole, this feature becomes especially pronounced because the differences in gravitational potential between different points become significant. But what precisely does this look like from an external vantage point? What does an observer see who is watching an object approach the horizon? Under ordinary conditions, light travels in straight lines, if we disregard obstacles. In a more precise description, it always follows the geometry of space, and near massive objects that geometry changes, forcing light to travel along curved trajectories. This is not the result of interaction with matter, but a property of the structure of spacetime itself. Therefore, even in a perfect vacuum, the trajectory of light can change noticeably. Near a black hole, this effect becomes especially pronounced. Light emitted near the event horizon not only changes direction, but also loses energy in the attempt to travel a great distance. For a distant observer, this manifests as a decrease in signal frequency. The light reddens, its wavelength increases. The light itself does not lose energy in a local sense. In every local region, its properties remain ordinary, and the change arises only upon comparison between different regions of spacetime. As the light source approaches the event horizon, the redshift becomes ever more substantial. A signal emitted near the black hole arrives to the distant observer ever more stretched in time and ever more attenuated. Imagine, you are watching a ship approach the event horizon. It slows, it dims, it reddens. In your time, it never reaches the boundary, and aboard that ship, everything continues entirely as normal. If we examine 1 hour of processes near a black hole, its image for the outside observer will depend on how close to the horizon the signal source was. The closer that source, the more time will be needed for the signal to reach the observer, and the more stretched it will appear. In the limit considered in the theoretical model, a signal from a region very close to the horizon becomes so stretched and attenuated that it is impossible to distinguish from background. And from a scientific standpoint, this means not the disappearance of the event, but the loss of informational accessibility for the outside observer. The motion of objects near a black hole is described through geodesic lines, the straightest paths in curved spacetime. In ordinary physics, motion seems simple. An object has a trajectory that can be represented as a line in space, changing over time. In a strict description, this line is called a world line. It connects events in spacetime, showing both where and when the object is located. But near a black hole, space and time cease to be independent entities. They form a single geometric whole, and the motion of an object is determined not by the familiar force of attraction, but by the geometry of that whole. Objects experiencing no external influence travel along geodesic lines, which near a black hole turn out to be strongly curved. Even if the object moves in a locally straight direction, its path as seen by a distant observer may appear complex and counterintuitive. As one approaches the event horizon, the geometry becomes so altered that the distinction between spatial motion and temporal progression begins to blur. The direction forward in time and the direction inward toward the center turn out to be linked. In a certain region of space-time, all possible future directions of motion turn out to be directed inward, not as a result of external influence, but as a result of the geometry itself. For the local observer, the motion of an object during 1 hour may look entirely ordinary. The object covers some distance, interacts with its surroundings, continues to exist in an unbroken sequence of events. For the distant observer, however, the description of this path becomes more complex. Owing to time dilation and gravitational redshift, the external picture of the motion begins to distort. Different parts of the trajectory may appear stretched, and the rate of change of position may seem to diminish. So what is speed near a black hole? And what precisely is the horizon? A physical wall or something fundamentally different? In ordinary life, speed seems a simple quantity, the ratio of distance traveled to time. But this simplicity rests on a hidden assumption that space and time are the same for all observers. And in conditions of strong gravity, this assumption ceases to be accurate. Speed is defined through the measurement of distance and time, but near a black hole, both distance and time depend on the position of the observer. Therefore, speed ceases to be a universal property of an object and becomes a quantity dependent on the method of measurement. A local observer situated near a moving object measures its speed using his own clocks and instruments, and for him that speed may remain entirely ordinary. The distant observer, however, will record a different value. Owing to gravitational time dilation and the curvature of light trajectories, measurements will diverge from local ones. This difference between local speed and observed speed at a distance is especially noticeable near the event horizon. Signals used to measure motion begin to be distorted ever more strongly, and light carrying information about the object's position arrives with delay and at an altered frequency. As a result, the outside observer may see the object appearing to slow, though this slowing is not an actual slowing of motion in the local sense, but merely a consequence of how the incoming information is changing. If one examines 1 hour of motion near a black hole, then throughout that interval, the object's local speed may remain quite stable. But for the outside observer, the description of that speed will depend on how signals travel through curved spacetime. As one approaches the event horizon, an effect arises whereby the outside observer registers ever stronger slowing of motion, not because the object's dynamics have changed, but because the signals describing its position are becoming ever more stretched in time. In general relativity, there exists no single universal value of speed identical for all observers in any situation. Speed always pertains to a specific frame of reference. Near a black hole, this becomes especially evident. Different observers in different gravitational conditions interpret the same motion differently. The speed of light, meanwhile, remains the limiting quantity for local measurements. Regardless of how strongly spacetime is curved, the local observer always measures the speed of light as constant. However, when comparing measurements between different regions of spacetime, effects arise connected with how precisely light propagates and is received at a distance. And these differences do not violate the internal consistency of the theory, but reflect the dependence of measurement on the geometry of spacetime. During 1 hour near a black hole, the local speed of processes remains defined and continuous, but the outside observer may interpret those processes as slowed or altered because of signal distortions. Speed ceases to be a simple property of motion and becomes part of a more complex structure of measurements that depend on the position of the observer. Causality, meanwhile, preserves its stability. Even if different observers measure speed differently, they arrive at no contradictions regarding which events can influence one another. The event horizon cannot be touched. It cannot be detected locally. It is defined not by what is present here, but by what can never make its way outward from here. This is a boundary drawn by causality itself. In ordinary perception, a boundary is usually understood as a surface that can be crossed. But the event horizon is not a surface in the ordinary sense. It does not exist as a material structure. It cannot be touched or measured as an object, nor detected by local influence. The horizon is defined differently, through the behavior of light and causal connections. It is the boundary separating regions of spacetime from which signals can reach an outside observer from regions from which such signals can no longer be received. The event horizon is not a physical wall, but a geometric property of spacetime. If one imagines 1 hour near a black hole, the key question consists not only in how long that hour lasts, but in which events from that hour can be observed from outside. Before the event horizon, signals are capable of leaving the region and reaching a distant observer, though with distortions, delays, and alterations of frequency. As one approaches the horizon, these signals become ever more stretched and attenuated. At the horizon boundary itself, in the theoretical description, a limiting situation arises. Light directed outward ceases to increase its distance from the black hole in the coordinate sense employed by the outside observer. It is important to understand that this is not a stoppage of light in the local sense. Locally, light always travels at the same speed, but the global geometry of spacetime makes the outward path unavailable. From the perspective of the outside observer, an effect arises whereby any processes occurring ever closer to the horizon appear ever more slowed and ever less accessible to observation. For the local observers situated near the event horizon, there is no special moment of crossing accompanied by a physical signal. If he is in freefall, his own time flows evenly, and no local boundary abruptly altering the laws of physics will he find. This difference between the external and internal description is fundamental. The event horizon is defined not by local measurements, but by the global structure of causality. It depends on which light paths are capable of connecting different regions of spacetime. The event horizon is not a place, but a relation between regions of spacetime. If one considers 1 hour spent near a black hole, its significance for the outside world is determined by whether that hour was spent before the event horizon or in its immediate vicinity. Before the horizon, information can be received, though with distortions. Near the horizon, it becomes ever less accessible. Beyond the horizon, in the framework of the classical description of general relativity, information cannot be transmitted outward, and events become causally isolated from the outside world. In deeper theories that include quantum effects, the question of information preservation becomes more complex and remains open. Interestingly, the horizon itself has no fixed position in an absolute sense. Its description depends on the entire history of spacetime, and its position is determined not only by the current state, but by how the system develops as a whole. The event horizon is a global, not a local, object. And what happens to matter that nonetheless crosses this boundary? From outside, it appears to freeze forever, a dimming image on the edge of eternity. From within, it simply continues its motion. In general relativity, the motion of a falling object is described as free motion along a geodesic line of spacetime. The object experiences no braking force in the familiar sense. Its motion is determined by the geometry of the surrounding spacetime. If an object begins its fall from far away, it gradually gains speed relative to an outside observer. But this description depends on the chosen frame of reference, and locally the object itself experiences no rupture or transition into a special regime. As one draws nearer to the black hole, the external description begins to change. Light carrying information about the object's position arrives with ever greater delay. Each successive signal places the object ever closer to the event horizon, yet never records its crossing within a finite external time. Because of this, an impression is created as though the object is slowing and never reaches the boundary. But this impression is connected not with the motion itself, but with how information reaches the observer. If one considers 1 hour spent by an object near a black hole, then locally that hour will consist of uninterrupted processes. All internal changes, atomic, molecular, structural, will proceed in their ordinary sequence. But the outside observer will receive information about that hour in a distorted form. Signals will arrive ever less frequently, their energy will diminish, and their interpretation will become ever less definite. As one approaches the event horizon, the last observable moments appear stretched across ever greater amounts of external time, and the outside observer gradually loses the ability to reconstruct the complete picture of what is occurring. The word disappearance in a strict scientific sense does not here mean the instantaneous cessation of processes. It means the loss of accessibility of information about them. Locally, the process continues. Externally, it becomes ever less observable. In the classical description of general relativity, the crossing of the event horizon is not accompanied by a local physical event that could be registered as a special moment. For the falling observer, there is no wall, no blow, no sharp alteration in the laws of physics. This is a consequence of the equivalence principle. In a small region of spacetime, the laws of physics retain their familiar form. But the outside observer cannot receive a signal that the object has crossed the horizon. In his frame of reference, the object becomes ever more slowed and gradually passes beyond the bounds of observability. A divergence arises between two descriptions of one and the same process, the internal and the external. The internal description is the continuous passage of time and processes with no special events at the horizon. The external description is the gradual disappearance of information and the asymptotic approach to the boundary without its being crossed within observable time. Both pictures are consistent within the theory because they pertain to different modes of measurement and interpretation of spacetime. 1 hour near a black hole can fit entirely within a finite interval of local time, yet its reflection in the outside world may stretch to a very large interval. The closer to the event horizon that hour takes place, the stronger the difference between the local and external description becomes. The concept of disappearance should not be understood as the physical annihilation of matter in the local sense. It pertains only to the limitation of access to information for the outside observer. Physical processes do not require observation to continue. They develop according to their local laws, regardless of whether an outside observer can record them. And what happens next, beyond the horizon? Inside the horizon, even the notion of staying in place ceases to function. The future is always a direction toward the center, not because something pulls, but because the geometry of spacetime leaves no other options. The inner region of a black hole, that part of spacetime lying beyond the event horizon, is not directly observable. Everything known about it follows from the mathematical solutions of the equations of general relativity and from the indirect logical consequences of those solutions. Therefore, any description of this region always has the character of a model, not of direct experimental observation. In classical theory, space and time inside the event horizon behave differently from outside. One of the key features is that the direction we ordinarily call inward ceases to be merely a spatial direction. Inside the horizon, motion in the direction of decreasing radial distance becomes an unavoidable part of the future. This is not the result of external influence, but a consequence of the geometry itself. Inside the event horizon, all possible future trajectories point toward the center, and this means that the notions of stopping or staying in place lose their familiar meaning, not because the laws of physics disappear, but because the very structure of available directions of motion becomes different. For a local observer crossing the event horizon, this transition is not accompanied by any sharp physical effect. At small scales, space looks ordinary. The laws of physics retain their form. But the global structure of spacetime no longer permits return to the outside, nor even remaining at a fixed distance from the center. In this sense, the event horizon is not a place where something happens. It is a boundary beyond which the set of accessible future states becomes restricted. Locally, 1 hour continues just as any other. Biological, physical, and chemical processes experience no instantaneous rupture at the event horizon. But after its crossing, that hour already belongs to a region from which it is impossible to transmit information outward. And for the outside observer, that time interval becomes fundamentally unavailable for complete reconstruction. In the classical picture, inside the horizon, the future, in a certain sense, narrows toward the direction leading to the central region. The term center is used here as an element of the model. In the classical description, the central region corresponds to the so-called singularity, a point or region where the curvature of spacetime becomes infinite in the framework of the equations of general relativity. Here is where the limit of applicability of the classical theory arises. It is considered that in this region, the effects of quantum gravity should manifest, effects that as yet have no complete theoretical description. Science does not claim that the singularity literally exists as a physical object. It indicates that the current theory ceases to be applicable in this limit. This is not an error of the theory, but an indication of its boundaries. Inside the event horizon, local causality is preserved. Events follow one another in strict order, and the local laws of physics continue to operate. But the global structure of causal connections becomes closed in such a way that exit outward becomes impossible. If one imagines an observer who has crossed the event horizon, his 1 hour continues to exist as a sequence of events, but that hour can no longer be compared with external time through the transmission of signals. The outside observer loses access to information after approaching the horizon. The inside observer continues his motion within the framework of local physics, but now without the possibility of communicating this to the outside world. A black hole in this sense is not an exception to the rules, but an extreme example. It shows that the observability of the world is always limited by the structure of spacetime. We do not have access to the entire universe simultaneously. We have access only to that part of it from which signals manage to reach us. This limitation is not technical. It is built into physical reality itself. Every observation is the receipt of information through signals, most often through light. Light propagates at finite speed, and its motion depends on the geometry of spacetime. Therefore, the observed picture is always the result of signals passing through this geometry. Near a black hole, this becomes especially evident. Regions too close to the event horizon gradually cease to contribute to the observed picture of the outside world, not because they disappear physically, but because information about them ceases to be accessible. Before the event horizon, 1 hour can be partially reconstructed by an outside observer, though with distortions. As the horizon draws near, reconstruction becomes ever less complete. Beyond the horizon, within the framework of classical theory, reconstruction is impossible. The observable universe is not a fixed volume of space, but a region of causal accessibility that depends on the position of the observer and the structure of spacetime. In a broader context, one may note that the entire observable universe has its own horizon, a cosmological limit beyond which signals have not yet been able to reach the observer, owing to the finite age of the universe and its expansion. A black hole is a local example of what in cosmology manifests on a large scale. The limitation of observation constitutes a fundamental characteristic of the physical world. 1 hour next to a black hole is not a universal unit identical for all observers. It is a local interval existing in a specific region of curved spacetime. For a distant observer, that hour may be stretched, distorted, or partially inaccessible. For the local observer, it remains an ordinary, sequential process. The difference between these descriptions is not a contradiction. It is a consequence of the fact that space and time form a single structure, and information about events propagates through this structure at finite speed and with changes that depend on the geometry. A black hole does not violate the laws of physics. It manifests them in their extreme form, where familiar, intuitive notions turn out to be insufficient. And it is precisely for this reason that its study matters. It shows where the applicability of everyday concepts ends and the necessity of a strict geometric description of the world begins. Please write in the comments how you found this story. It truly matters to me to understand whether it captured you and whether you felt behind the words about the event horizon and gravitational redshift, that quiet boundary where our ordinary notions of time no longer function. What do you think? Does an observer who has calmly decided to approach the event horizon in search of information about the geometry of spacetime act wisely? Or is this a path from which no one ever returns? And one more thing. Do you find it more comfortable to watch the video in horizontal or vertical format on the phone?